Hi guys, I'm just getting ready to tape our lesson from section 6.3. So let me just get it going here. All right, so 6.3, graphing to solve systems of linear inequalities. The objective of this lesson is to understand what it means to model systems of linear inequalities so that we can use them in problem solving. So we're going to have these word problems that are fairly complex situations, and we're going to try to solve them by using these models of linear inequality systems. Now, last year you did learn how to solve systems of linear equations. And just in case you've forgotten that, what that means is you will have two equations that belong in the same graph. You have x's and y's that you're missing. And so we talked a little bit in class about the different ways that you solve this. And I think eventually it came back to you. You remembered that you could do this by elimination, or you could use substitution, or you use something you called comparison. And what you were using there in trying to solve these guys, if you were to actually graph it, these two lines, this line and this line, what you're looking for is where they intersect. So let's take a look at the actual question and see what we can do with it. Now, before we can actually go ahead and draw the graph, we need to move these equations around. And so you'll notice below that I've taken these two equations and I've shifted them around so that y is equal to whatever is on the other side, the slope and the intercept. Now, I would encourage you, as I always do when you're doing these videos, to stop and pause and try this for yourself. Make sure that you end up with your equations looking the same. Now, if you were to graph these, let's take a look at this one. You need an intercept of 1, here he is, and you need a slope of 2. So we're going to go up 2 and over 1. That's your first line. This one, you have an intercept of -2 and a slope of -1. So you go down 1 and over 1 and draw your line. And what you notice is that the two lines intersect at -1, -1. So the solution to this systems of linear equations is -1, -1. Now this year we're going to add to that, and we're going to use what we've been learning about linear inequalities to do the same thing. So we're going to take systems of linear inequalities where we have shading, and we're going to try to look for where the shaded parts overlap each other. So we're going to try a question like this one. So we have three different linear inequalities, and we're going to draw them on the map, on a graph, and see what happens. So we're going to try some examples. Let's start with this one. So the first one is x is greater than or equal to 0. Well, we know that x is equal to 0 at the y-intercept. So I'm going to draw a line right there. And all of the points that are greater than that line would be on the right-hand side. So it would look something like this one in red. Next one I'm going to do is y is greater than or equal to 1. So now I'm going to be drawing a horizontal line, and then I'm going to fill up top. And so there you have it. And so far you can see that this is where it's overlapping. All right, now we need to take care of this guy. So we're going to have to move this equation around and get y by itself. Move your 2x over. So you're going to have an intercept of 4 and a slope of -2. If you look at that, here's your intercept of 4, a slope down 2 and over 1. That creates this green graph. Now the green line, you notice, is dotted because it isn't equal. And we're being asked to do where the y values are less than this line. And as you look at the y values along here, they're smaller than your line, whereas here they were larger. So I draw my line and I color it. Now, after a while, it does get a little bit messy trying to see this, but we've looked at this one in class and we can tell that this little triangle right here is where all three colors are found. You've got the blue, you've got the red, and you've got the green all together in that mess right there. Okay, here's another one to try. And again, I would encourage you to pause the video, try it yourself, see if you can get through it, and then you can look at the answers that you see online. Now, of course, what we need to do first is take this equation and move it around. So I'm isolating for y. And then I'm going to draw a line that looks like this one. Just peek at this for a sec. Yep, here it is. An intercept of 4. Notice I'm using a dotted line and a slope of down 1 and over 2. Now I'm being asked to shade where y is less than this line. So all the y values along here are smaller than the line on this side. So I shaded it. Let's take a look at the next one. So then we have to take this guy and we have to isolate it. Now this time when you move your 3x over, it's negative 3x. But remember you have a negative y here. So you got to divide everybody by a negative. So your sign, oops, with mine, I can see that it should have been greater than or equal to right there. I can fix that later, but just this should be an equal sign. So when I draw my graph, I should have a solid line there. So let's see what I did. Yeah, for the actual drawing, I actually did it right. So my intercept is 6. My slope is 3. Now, I've run out of room up here. So what I could do is I can go down 3 and to the left 1, and that gives me my slope. So once again, what I'm looking for is where the two overlap. So this region right here, which is kind of like a funny shaped, what is it? 1, 2, 3, 4, 5, five-sided figure. This spot that we see. Now we're going to take a look at word problems, and we always are aware that the word problems are the toughest ones. But don't give up and just keep trying. There are a couple of hints that I've given to you here. When you have lots and lots of numbers crowding up the question and you can't think anymore, one thing you can try is look for that final explanation, the final question, and usually that tells you which variables you should be looking for. And then always pay attention to a number. It may seem unimportant, but always look at it and make sure that it may or may not be a part of your question. So we did this one in class, and this was the question about a sporting goods manufacturer who makes footballs and soccers. It tells us how long it takes to make a football. You have to put on a cutting machine for 3 minutes and a stitching machine for 1. Then you have a soccer ball. It's on the cutting machine for 3 and the stitching machine for 4. So the question is, what combination of balls can be made in 1 hour or less? Now, this sentence is the most important thing because we want to know the combination of balls. And so we're going to call footballs and soccer our X's and Y's. So here you have it. X is the football and Y is the soccer. Now, after that, we have a couple of bits of information. We've got information about how much time these things take on the cutting machine and how much time they take on the stitching machine. So if you think about it, you've got 2 machines going for an hour. The time here could add up to 60, and the time on the stitching machine could add up to 60. So you'll see that I created equations that show I had to take 3 minutes on my football and 3 minutes on my soccer, and it's going to go to 60. It may be less, but it can't be more. And then the stitching, it takes 1 minute on the stitching machine for the football. Make sure I did that right. Yes. And 4 minutes on the stitching machine is for the soccer ball. Now, what I've done to make it a little simpler was I decided I would just find the intercepts for these, and I didn't actually show you the work, but I'm hoping you can do that yourself. I'm going to find the y-intercept and the x-intercept so that I can graph it easily. Same thing over here. Now, I take those bits of information and I'm graphing them. So there's my intercept 20 to 20. Here's 60 to 15. And I can tell that they're overlapping in all this section. But keep in mind, we are talking about real things here, real footballs and soccer balls. So I'm never going to use anything past the y-axis or the x-axis. It's just this little spot. Now it says what combinations of balls can be made in 1 hour or less. Any of the points, let me find any of your points in here would be possible answers. Like you could say, these go over, I guess, by 2 points. So here's 2, here's 4, and we could go up in 6, and we could say, all right, 4 footballs and 6 soccer balls would work. And sure enough, it'll be made in 1 hour or less. Or we could use 2, 4, 6. No, that isn't quite. Sorry, I'm just realizing these are quarter marks. So this is 2.5 and that's 5, 7.5 and 10. So better do that again. We could do 5 and 5. We could do 5 and 7.5, but we said that we didn't really want half ones. So 5 and 10. You could do 5 and 15. So you could do 10 and 10. So there are a variety of possible answers that we could have for this one once we see our diagram. Okay, now this one. This one is a bit of a confusing word problem because of the actual context. It's talking about sailing. If you've had the privilege of learning how to sail, this will make more sense to you. But a sloop is a sailboat with two sails. So it's got the mainsail and what they call the jib. So when a sail is fully out or up, it's said to be out 100%. So when the winds are really strong, sailors often do a condition that they call reefing, or they pull it in so the sails are less than their full capacity. So Jim is sailing in winds of 22 knots. So he wants no more than 90% of the jib, and he wants at least twice as much jib as mainsail. So that just sounds like a foreign language sometimes, but don't despair. Go to the main question. What possible combinations of mainsail and jib can Jim have out? So we can tell, all right, the things we're going to call X's and Y's are right here. So let's get it set up. I called X the jib and Y the mainsail. Now, if I look at it, it's here. He wants no more than 90% of the jib. So it could be 90% or less. So X, the jib, is less than or equal to 90. Then he says he wants to have at least twice as much jib. So the X is going to be 2 times bigger than the mainsail. X is greater than, and he says at least as much. So X is greater than or equal to 2Y. This one we need to fix a little bit because this is not really in our format. Let's flip sides. And if we do, then we have to keep it the same way it was before where X was bigger. So 2Y is less than or equal to X. Divide by 2 and you have your second equation. So we're going to use this one and this one on our graph. So if you take a look at it, we have X is less than or equal to 90, the red one, and Y is less than or equal to 1/2 X. So this guy has an intercept of 0 and the slope is up 1 and over 2. So that's the blue one. So we can see that our overlapping parts are this triangle right here. And I'm going to simply ignore the negatives because we can't have negative amounts of the sail in or out. So what possible combinations of the mainsail and jib? Keeping in mind that the X's are the jib and these ones are the Y's. So I could say 50 jib and 20 mainsail, or I could say 70 jib and 30 mainsail, or 80 jib and 40 mainsail, and so on. All right, you can pick all kinds of combinations within this part that's overlapping and greater than 0. Okay, so that's it. Solving problems by modeling systems of linear inequalities. Good luck with your homework, everyone. Make sure you bring your questions to class. This is your homework, and so if you haven't already seen it on the Google Classroom site, here you have it in front of you. Okay,